Hi friends, in this class we are going to discuss about the capacitance of a parallel plate capacitor. The capacitance of a parallel plate capacitor, for saying that we will have to consider a parallel plate capacitor which is connected to a battery as shown in figure. You can see a parallel plate capacitor. This is our parallel plate capacitor. It is connected to a battery as shown in figure, and if it is connected to a battery as shown in figure, there will be a positive charge induced over here and a negative charge induced over here. As a result, there will be an electric field developed between the plates of the capacitor. The electric field developed between the plates of the capacitor, in this case it will be from positive charge to negative charge. This is the direction of electric field, and we have learned it in our previous classes, that is electric field between the plates of the capacitor in this case is sigma by epsilon 0. This is the electric field developed between the plates of the capacitor. And what is sigma? Sigma is surface charge density. Epsilon 0 is permittivity of free space. And on speaking, these are the two plates of the capacitor. The plate area of the capacitor is A. The area of the two plates of the capacitor is A, and the distance between the plates of the capacitor is D. What was sigma? Sigma was surface charge density, and since sigma is surface charge density, we could write surface charge density as charge per unit area. Therefore, sigma is equal to Q by A. Then I could rewrite the electric field intensities expression as, instead of sigma we are substituting Q by A. Therefore, Q by A epsilon 0. This is another expression for electric field intensity. Then we know, or we have learned a relation, that is electric field intensity is the negative gradient of potential. We have learned E is equal to minus dV by dx, or in other sense we could write from this, we could write dV minus dV is equal to E dx, or potential is equal to electric field intensity into distance of separation. That is, in the case of capacitor, we could use a relation, that is potential difference is equal to electric field intensity into distance of separation. Therefore, in this case we could write V is equal to electric field intensity into distance of separation, it is D. And if we are substituting the value of electric field intensity over to this, we will get V is equal to Q by A epsilon 0 into D. This is the expression for potential. Then we know a basic relation, that is C capacitance is equal to Q by V. Capacitance is the ratio of charge and potential. This is the basic relation of capacitance. C is equal to Q by V. And if I am substituting that in our current equation, C is equal to Q into 1 by V, that is Q into reciprocal of this A epsilon 0 divided by QD. We could cancel these Q's. Q could get cancelled, and finally we will get C is equal to epsilon 0 A divided by D. This is our expression for capacitance of a parallel plate capacitor. C is equal to epsilon 0 A by D, where epsilon 0 is permittivity of free space, A is plate area of the capacitor, D is distance between the plates of the capacitor. From this relation we could understand the capacitance can be increased by increasing plate area and decreasing the distance of separation. What are the two methods for increasing the capacitance? Increasing the plate area and decreasing the distance of separation. Hope you have understood this. Okay, in the previous session we discussed about the capacitance of a parallel plate capacitor. This is the mathematical derivation for that, and now in this session we are going to discuss about the capacitance of a parallel plate capacitor with dielectric. That is, we are having a parallel plate capacitor over here. This is our parallel plate capacitor. As in the previous diagram, we could imagine it to be connected with a battery as shown in figure, and the specifications are: the plate area of the capacitor is A, distance between the plates of the capacitor is D. In this case, we are filling the space between the plates of the capacitor with a dielectric. Dielectric is an insulating medium which is added between the plates of the capacitor. What's a dielectric? Dielectric is an insulating medium which is added between the plates of the capacitor. The reason for adding the dielectric between the plates of the capacitor is in order to increase the capacitance of capacitor. The reason for adding dielectric, that is insulating medium between the plates of the capacitors, in order to increase the capacitance of the parallel plate capacitor. And in this case we are adding a dielectric which is having a dielectric constant K. K is the dielectric constant of the dielectric that we have added between the plates of the capacitor. In this case also we have to understand the capacitance of the parallel plate capacitor. For that we will be proceeding as we have proceeded in the parallel plate capacitor without dielectric, in the same manner. And if this is connected like this, we will have a positive charge induced on this plate, negative charge induced on this plate, and as we have proceeded in the first case, we could say there will be an electric field induced, and that electric field will be what? That is, let me start from here. That is, we know potential is equal to electric field intensity into distance of separation. As we have proceeded in our previous derivation up to this, I am starting from here. That is, potential developed will be electric field intensity into distance of separation, and I will write this as V is equal to E medium into D. That is, in this case the electric field intensity is electric field intensity inside a medium, but in the previous case this was electric field intensity in air, but in this case it is electric field intensity in medium. And if we are recalling an expression for force, we have studied that force in medium is equal to force in air divided by epsilon r. We have learned it in our basic classes of electrostatics. That is, Coulomb's law. We have learned force in medium is equal to force in air divided by epsilon r, and this epsilon r is permittivity of medium, relative permittivity, or dielectric constant. In this case we will denote epsilon r by a letter K, and that letter K is represented over here. K is dielectric constant. By dielectric constant, what you should understand is dielectric constant is epsilon r itself, but in this case we are representing epsilon r as dielectric constant K. Therefore, force in medium is force in air divided by epsilon r. Likewise, we could say electric field intensity in medium is equal to electric field intensity in air divided by epsilon r. If force in medium is force in air divided by epsilon r, we could write electric field intensity in medium is electric field intensity in air divided by epsilon r. We could write E air, I am denoting E air as E divided by K. Therefore, we could use that information in this derivation, that is V is equal to, instead of electric field intensity in medium, we are writing E air divided by K into D. And in our previous derivation, we have learned E air is sigma by epsilon 0, and substituting for sigma, we know E air is Q by A epsilon 0. Therefore, I am directly writing it over here, where electric field intensity in air is Q by A epsilon 0. Electric field intensity in air is Q by A epsilon 0. Therefore, we could write electric field intensity in air as Q by A epsilon 0. Remaining thing in this expression is D by K. Therefore, QD by A epsilon 0 K V. And from V, we could find C, that is, we could write the basic expression of capacitance. C is equal to Q by V. If C is equal to Q by V is the basic expression of capacitance, we could write it is equal to Q into 1 by V, and substituting for V, Q into 1 by V means reciprocal, that is A epsilon 0 K divided by QD, from which Q will get cancelled and C is equal to K epsilon 0 A by D. This is capacitance with dielectric, that is capacitance with a medium. Therefore, we are getting the expression like this. And if we are comparing this capacitance with medium expression with capacitance with air was epsilon 0 A by D. Capacitance with medium is K epsilon 0 A by D. And we could clearly understand this value will be capacitance with air. Capacitance with air. Therefore, we could write capacitance with medium is equal to K into capacitance with air. And if a dielectric is introduced into the parallel plate capacitor, the capacitance will increase by K times. We could understand that capacitance in medium is K times capacitance in air. And if there is a question coming, what are the methods for increasing the capacitance of a parallel plate capacitor? What are the methods for increasing the capacitance of a parallel plate capacitor? We have to say, by introducing a dielectric with a high dielectric constant. One method, introducing a dielectric with high dielectric constant, increasing the plate area of the capacitor, decreasing the distance between the plates of the capacitor. Therefore, capacitance of a parallel plate capacitor without dielectric is epsilon 0 A by D. Capacitance of a parallel plate capacitor with dielectric is K epsilon 0 A by D. Hope you have understood this derivation. Hi friends, in this session we are going to discuss about the capacitance of a parallel plate capacitor if the dielectric is partially filled. For that, let's consider this diagram. This was the diagrammatic representation of a parallel plate capacitor which is not having any dielectric, and distance between the plates is D, plate area is A, we were getting an expression for that as C air is equal to epsilon 0 A by D. Now, if we are analyzing this diagram, we could see this is the diagrammatic representation of a parallel plate capacitor which is completely filled with dielectric, and we were obtaining the expression of that as C medium is equal to K epsilon 0 A by D. Now we are going to speak about a diagram like this. The peculiarity of this capacitor is the plate area of the capacitor is A. Distance between the plates of the capacitor is D. And we could see a dielectric over here and we could see a dielectric over here. The difference is this dielectric is completely filled between the plates of the capacitor. But in this case, the dielectric is not completely filled. It is filled up to a thickness T. It is filled up to a thickness T. The dielectric constant is K. Now we have to solve the mathematical simplification of this. For that, let's have the derivation. We will proceed our derivation just as the way we have proceeded in the previous derivation. For that, initially we will find out the potential, then we will find out the capacitance. But in this case, I'll start it with like this, that is total potential between the plates of the capacitor. It will be potential developed where there is air plus potential developed where there is a dielectric. That is, the region between the plates of the capacitor is having air and medium. The potential over air plus potential over medium will give you the total potential. Then, as we know, potential is equal to electric field intensity into distance of separation. We could use total potential V as potential in air will be electric field intensity in air into distance where air is there between the plates of the capacitor. Is D distance completely with air? No. This region is with air, therefore air is over a thickness of D minus T. Therefore, potential is equal to potential in air is equal to electric field intensity in air into D minus T plus potential in medium can be written as electric field intensity in medium into distance where medium is present. The medium is present at a distance of T. This is, we have studied potential is equal to electric field intensity into distance of separation. Therefore, potential in air will be electric field intensity in air into distance where air is present, that is D minus T. Potential in medium will be electric field intensity in medium into distance where medium is present, that is T. Clear? Then we already know electric field intensity in medium is equal to electric field intensity in air divided by K. We have studied it in our previous derivation. Therefore, we could write potential is equal to electric field intensity in air, we are writing it as such, into D minus T plus electric field intensity in medium can be replaced as electric field intensity in air divided by K into T. Clear? From which we could take electric field intensity in air out, then the remaining thing is D minus T plus T by K. Then we know electric field intensity in air is from our derivation of parallel plate capacitor. Electric field intensity in air is Q by A epsilon 0. Therefore, it is Q by A epsilon 0. Therefore, Q by A epsilon 0 into D minus T plus T by K. This is potential, and from the potential we could find out the capacitance. The basic relation for capacitance is C is equal to Q by V. If C is equal to Q by V means we could write Q into 1 by V. Therefore, substituting for C in this equation, we could get C is equal to Q into 1 by V means the reciprocal of this. Denominator we are having A epsilon 0. It will come to the numerator A epsilon 0. In the numerator we are having Q and this complete thing in the bracket. Therefore, in this case we have to write it in denominator Q into T minus T plus T by K. Clear? Reciprocal. Q and Q will get cancelled and ultimately we will get C is equal to epsilon 0 A divided by D minus T plus T by K. And this is the expression for capacitance of a parallel plate capacitor if it is filled partially with a dielectric, or if the dielectric is filled up to a thickness T, where T is the thickness of the dielectric, K is dielectric constant, D is distance between the plates of the capacitor. If you are going for a quick comparison, electric field intensity in air was epsilon 0 A by D. Electric field intensity in medium, that is if the capacitor is completely filled with medium, it was K epsilon 0 A by D. And if the capacitor is filled with a dielectric up to a thickness T, it is epsilon 0 A into D minus T plus T by K.